All right. Welcome everybody back to our the second of our Distinguished Alumni Colloquium series in celebration of our 100th anniversary as a department. Today's speaker is Scott Kenyon. He's a scientist at Harvard-Smithsonian Astronomical Observatory, and he's got a very distinguished career. He, of course, started at Illinois he did his PhD with Ron Webbink in 1983, working on symbiotic stars. I think most astronomy theses don't necessarily turn into a whole book, but this one did, and one of the definitive references on symbiotic stars. And he's worked a lot in formation of star systems, protoplanetary disks, and the formation of planetary systems. And he's the recipient of several awards. He's a fellow of the American Physical Society and the AAAS. He shared the Hoops Prize with Jane Liu and Sarah Stewart in 1995 and the Copernicus Medal in 1987. And so we're very glad to have him here, and I guess he'll share some reminiscences toward the end of his talk. But today he's going to tell us about how Pluto, didn't take its demotion from planet status lying down. So please go ahead and take it away.
Well, thank you very much for that great introduction. I wish I could be there with you, but that's not possible at the moment. So I hope that's visible. If it's not visible, please let me know. And it's a pleasure to be able to speak to Illinois. I had a lot of great years at Illinois, 5 of them. I will say a little bit about that at the end of the talk. I did write a poem for the virtual meeting in August. Hopefully that's around somewhere, so I don't have to read it again. But that contains a lot of my memories of Illinois. And so today I'd like to describe some work that I've done with Ben Bromley at the University of Utah. And I title it Pluto Strikes Back because I think that Pluto has been maligned in many ways. I think that I'm not going to take a stand on whether or not it should be a planet because I sort of go with Gertrude Stein, who said a rose is a rose is a rose. And so we will start with the discovery of Pluto. And as you probably recall, in the middle of the 19th century, once they were analyzed with Newton's laws, it led pretty quickly to the discovery of Neptune. And after Neptune's orbit was defined fairly reasonably well, it took a few years, but Percival Lowell used the same technique, wiggles in the orbits of Uranus and Neptune that weren't explained by the masses of the known planets to predict the existence of Pluto. It took a bit longer to find Pluto. It took about 15 years. And Pluto remained the only object beyond the orbit of Neptune until 1992, when Jane Liu and Dave Jewett discovered the first Kuiper Belt object. Over the next years, lots of Kuiper Belt objects were discovered. Here's sort of a rogues gallery of some of the largest ones. All of these are, of course, artist conceptions, but they give you an idea of the relative size. And what makes Pluto and these sort of distinctive is the orbits that they have. Here is an edge-on view of the solar system. The major planets are shown in little magenta ellipses that you can barely see. This large cyan ellipse is the orbit of Pluto. And these other little boxes, the cyan boxes, are the positions at the time when I made this plot of other Kuiper Belt objects. You can see that many of them are in the plane of the solar system, but many others are out of the plane and have orbits similar to Pluto. And Pluto takes 2 orbits around the sun for every 3 of Neptune. So it's in what we call a resonance and in fact, a 3-to-2 resonance. And many of these Kuiper belt objects are in other resonances, such as the 2-to-1 and the 5-to-3, and so on. Here's a set of orbits from the top, the view of the top. The sun is at the center. The white is the orbit of Jupiter, and then Saturn, Uranus, Neptune in blue. Pluto, again, is the cyan oval. You can see it goes inside the orbit of Neptune, and it goes well outside. Here are a bunch of Kuiper belt objects. And this magenta orbit indicates or the magenta ellipse indicates the orbit of what's called the scattered disk object. So it has a very highly eccentric orbit, and some of them have orbital eccentricities as large as 0.8 or 0.9. And so you can see that, you know, the consternation of lots of astronomers was, well, what do we call all these things? Are all these things planets? Are all these things dwarf planets? And so Pluto was demoted. And, you know, that's the way it is. Pluto's striking back begins in 2006. The HST satellite took a lot of images of the Pluto system in advance of the New Horizons flyby. New Horizons was on its way to Pluto at this point, but they wanted to make sure that they didn't hit anything as they passed through the system. So HST took a lot of images, and you can see two of the satellites here, Pluto and Karen in the center, very highly diffraction spikes there, Nix just below a diffraction spike, and Hydra farther out. And then in 6 or 7 years later, two more were discovered. And here is the set of satellites and Pluto and Charon. Pluto and Charon are binary, and this is in fact a binary planet, the only binary planet in the solar system. The center of mass of Pluto and Charon is outside of Pluto, unlike the Earth-Moon system. The mass ratio is around 1 to 10. Pluto and Charon are in a circular orbit. The eccentricity is less than 10 to the minus 5 in the latest measurement. And they orbit tidally locked. So the day on Pluto is equal to the day on Charon, which is around 6.5 days. The four satellites are almost exactly in the orbital plane of Pluto and Charon, within a degree or so. And their orbits are also nearly circular. There's sticks at the inner edge, almost to the innermost stable orbit around the binary, but not quite. Then there's Nix, a little bit larger, Kerberos, a little fainter, and Hydra. And so those are the four that were discovered before the New Horizons mission. And HST has discovered none since then. New Horizons went by Pluto. It unfortunately couldn't orbit. That would have been very nice. But these are a couple of the images from the mission. Pluto, you can see there's a sea made of nitrogen ice. There's some craters here and there. And here's an image of Charon with a very nice valley on the edge at around 2 o'clock or so. And relative to the diameter of Charon, which is about 600 kilometers, this is a deeper valley relative to the radius of the planet than the Grand Canyon is for the Earth. So that's pretty impressive. Charon also has a set of craters and sort of a sea-like thing. And here are the four satellites seen by New Horizons. Since they were flying by, they didn't have a chance to get the best images of either satellite or any of the satellites. They had to take what they could get. The flyby was just a couple hours. Nix and Hydra were closer. They're a little better defined. Styx and Kerberos were further away. But you can still see some interesting things with both Styx and Kerberos, that they look like sort of two ice cream scoops or two pyramids or whatever stuck together. Nix and Hydra are a little bigger, 20 kilometers across instead of 10. These things are extremely reflective. The lowest reflectivity is for, as I remember, Nix and Kerberos at 55%, Styx is 65%, and Hydra is 85%. So the surface of Hydra is almost a pretty good, astronomical mirror in terms of reflectance. And
Are the relative sizes sort of accurate here?
yes, Hydra and Nix are about 20 kilometers across. The aspect ratio for Nix and Hydra is about 3 to 2 to 1. So they're not round by any stretch of the imagination. Kerberos and Styx are about half, the diameter. If you make sort of a spherical average of everything, and they're also about 3 to 2 to 1. I mean, they're not exactly 3 to 2 to 1, but that gives you an idea that the shapes are very non-spherical. So the combined results from HST plus New Horizons, there are no new satellites. New Horizons did its best to find satellites inside the orbit of Hydra and found none larger than 2 kilometers. I mean, there could be 1,000 smaller than a kilometer scattered around the system, but none larger than 2 kilometers. The satellite masses are uncertain because there's no way to apply Newton's laws to them. The satellite origins are uncertain. And so the goal of the project that Ben and I started before New Horizons started its pass was to understand where could you find new satellites? Can we place limits on the masses? And can we understand the origins of the satellite in the context of the origin of the solar system? So I'm going to go through a few of the projects that we've done over the last 3 or 4 years to try to understand these issues in more detail. So I will start out with the satellite masses. I'll show you the results of some n-body calculations. What we do is we take the 6D phase space variables that HST gives us from the orbital fits. And so that's x, y, and z, vx, vy, vz. HST gave nominal satellite masses, which we've revised some to be more sensible given the densities of things. But anyway, we vary the satellite masses. We don't vary the initial phase space configuration, but we vary the satellite masses and we try to find out what's stable. So here is an example, 2 examples actually. On the y-axis is the barycentric distance in the, maybe not obvious, easy intuitive thing, but Pluto Radii, which is good for this kind of experiment. The evolution time in gigayears, I only show the last few bits of it. These are, the numbers to the right are the masses of each of the satellites. So Styx has a mass of 0.6 times 10 to the 18 grams. Nix is 67.5. Kerberos is 0.9, and Hydra is 48 times 10 to the 18 grams. And we just let the system go for 2 gigayears. It took a while to get to there, but you can see that for a long time, and prior to this plot, it looked about the same. So there's really not much interesting to show. There's some wobbling around for all of them, but there's not much going on until the last few tens of millions of years when Kerberos starts to vary its barycentric distance. It eventually finds itself in the Hill sphere of Hydra. And as soon as it finds its way into the Hill sphere of Hydra, Hydra says, "You're going away," and it is ejected from the system. In the top plot, we have, again, the same kind of configuration. These are the masses of the satellites. Here we make Hydra a little more massive. Styx and Kerberos have the same mass, and Nix is a little less massive. Here, it's a little bit more interesting. What happens dynamically is they sat around for a long time, close to 1.3 gigayears. Then Styx develops a little bit of perturbations in its orbit. Those perturbations grow. It almost crosses the orbit, the Hill sphere of Nix, but it pulls itself back, gets itself together for a little while. But in doing so, it started to excite a little bit of the orbit of Kerberos. You can see that its oscillations started to get to be a little bigger. And so Kerberos starts to oscillate a little more, but even though Styx rather got itself together for a little while, it eventually crosses the orbit of Nix and then is ejected from the system. And so by doing this for, it's close to 1,200 simulations now, we can get a pretty good idea of the mass of the system. That is, we understand which masses make the system unstable, and we can do that in a variety of ways to see in terms of which of the unfinished calculations might be unstable. This is a plot of the eccentricity dispersion in Styx. So what we do is we take the evolution, divide it up into pieces. We calculate the mean eccentricity of Styx, and we calculate the dispersion in the eccentricity in those little pieces. And here are 5 simulations along the bottom and another 5 along the top. For a long period of time, the dispersion is 0.009. But then, when Styx starts to have those variations in its barycentric distance, the eccentricity dispersion also grows. And it grows and grows until it gets to 0.02, and then it goes away. It is ejected. And you can see that the systems that we have here where we get up to an ejection all get to about 0.02 before the system is ejected. And when the eccentricity of Styx has a dispersion of 0.02, its eccentricity is large enough such that its orbital distance from its instantaneous distance from the barycenter allows it to cross Nix's Hill sphere. And so this is an actual the 0.02 is an actual upper limit on the eccentricity dispersion of Styx. And all the simulations that fail, where Styx is ejected, fail in this way. And you can see this black one, it goes for almost 3 gigayears before it does anything. But once it does something, it goes pretty quickly. The curves where you don't get up to 0.02, the orange and the light green one here and the orange and light green one here, those have not suffered an ejection yet. But you can see that this orange one is starting to go on its way. It had a little bit of a hiccup here, but its eccentricity dispersion is starting to increase. And based on these others, we would expect an ejection in the next 100 million years or so. So given our calculations, that's about a month from now. The green curve, the green dots rather, is pretty steady for 3.5 gigayears. So that system may end up being stable. The numbers up here are the fraction of the mass relative to the nominal masses of the satellites. We establish a set of masses, and then we vary those masses slightly. And this is 5 different multiplicative factors times the nominal mass of the satellites. And so you can see that small differences in that ratio can make large differences in a lifetime.
Scott, we've got a question. Michelle Giovacchini.
Sure.
Michelle, go ahead.
So I was wondering if this is like how certain are we that this is going to happen? Is it like we know that a moon is going to get ejected soon, or is it just like in the far future this might happen?
Well, what we're trying to do in this is understand what the masses of the satellites can be. So we know the dimensions of the satellites, but we don't know their density. And so if they have the density of Pluto and Karen, which is 1.75 to 1.7 to 1.85 grams per cubic centimeters, they're more massive than our nominal masses. And so our goal is to rule that out. But they could have a density of 1/10 of a gram per cubic centimeter, and we wouldn't know the difference. And they would have masses much lower than this. So what we're trying to do is get an upper limit on the mass of the system and ask what that means for the mass density of the system. So, these are n-body calculations. And so the conclusion that we have, since some of these with the nominal masses appear stable and some of them don't, is that the nominal masses are barely stable. And that provides an upper limit on the total mass of 10 to the 20 grams. So what we would say is if the mass in the system is of order 10 to the 20 grams, then it's barely stable. And so the moons could go away tomorrow, or they could go away, a gigayear from now. But based on our n-body simulations, roughly half of the systems with the nominal masses, this 10 to the 20 grams, will last for 4.5 billion years. Now, what does that mean? I hope that answers your question. If it doesn't, I'll continue on and try to answer it better. But if the mass were, say, 10 to the 19 grams for all the satellites, then they're nowhere near unstable. And so they'll last for as long as the solar system lasts. Implies an upper limit on the mass density of 1.25 grams per cubic centimeter, very close to, say, water ice. And here are the densities of Charon and Pluto, 1.7 and 1.85, which are not made of pure ice. They have some rock and other things. So what we would say, since the mass density has to be smaller than 1.25, is that the satellites are made of ice, which is what you get from the spectra and what you get from the albedo or the reflectivity. So we have a consistency argument that the satellites can't be any more massive than this. But as I said, they could be much lower mass and they would be stable for the next 5 gigayears. But if they're of order this mass, then they might be stable for the next 5 gigayears, or they might go away in the next gigayear. So that's our limit on the mass. We've progressed from the HST masses, which had some of the satellites having mass densities larger than 4 grams per cubic centimeter, to something reasonable on a limit on the mass density. So I'm going to switch now to search for new satellites in the system. Again, we do a set of n-body calculations with Pluto and Karen and the 4 satellites with these nominal masses, which we say are barely stable. And we put 15,000 massless particles around the system to see what survives. Here is the starting configuration. There's some overlap in our starting conditions of the different massless tracers. Here are these dots are the 4 satellites, Pluto and Karen here. And what I'm going to show you is a movie of snapshots of the system as a function of time. So it's not going to be a continuous movie because that can get a little confusing and can make you a little ill at times as things move around pretty quickly. But this will give you an idea of what happens over 10 million years. And so the thing we want to know is, are any of these massless tracers left after a reasonable amount of time? And so here we go. So, the tracers start to leave pretty quickly, in 1,000 years or so. The 4 satellites start clearing out, regions near their orbits. They have a hard time clearing out tracers that are co-orbital with them because the synodic period for those kinds of satellites are pretty long. But after 10 million years, you can see that there's not much left. There's a little bit inside the orbit of Styx, and this material is in between the innermost stable orbit, which is more or less sets the inner boundary here, and the orbit of Styx. Those might not last 4.5 gigayears. We didn't want to do the calculation any longer because I think we know what the answer is. There are a few particles in between the orbit of Styx and the orbit of Hydra. They won't last another, even a few million years. So we didn't bother running the calculation anymore. But there are lots of tracers left over outside the orbit of Hydra for Hydra's nominal mass. If Hydra were more massive, which we don't think is possible, this region would extend farther out. And the outer boundary of this region is artificial because that's where we put the tracers. Well beyond the outer boundary of these blue tracers, things are still stable. until you get to, essentially 10 times the orbit of Hydra, when the sun starts making things unstable. The gravity of the sun, the tides from the sun make things unstable. So based on this simulation, we would predict there were 2 places where you could have stable satellites in the system that are smaller and that escaped New Horizons, inside the orbit of Styx, which we think is unlikely, and outside the orbit of Hydra. And with JWST hopefully launching sometime this fall, the mid-infrared instruments on JWST can detect 0.5 to 1 kilometer satellites. And the field of view of these instruments is pretty well set for the Pluto-Charon system. So and there are approved programs for JWST to observe the satellites. And so, if it detects, 0.5 to 1 kilometer satellites at all, we would predict that they should be outside the orbit of Hydra and maybe a small probability inside the orbit of Styx. And if there are satellites detected in between the orbits of Hydra and Styx, either they're sort of temporary, or that sets a limit on, a new limit on the masses of the satellites, because if there are small satellites in between the orbits of the known satellites, the way we would interpret that is that the known satellites are less massive. Because I'll run this movie again, if these satellites were less massive, then they would clear out a smaller volume of their orbits. And so there would be more material left in between the orbits of the satellites. And so if they were, say, half the mass, then the regions between the satellites would be more filled. And in this simulation, that doesn't happen. And so if there did happen to be, a 0.5 kilometer satellite somewhere in through here, then we could place, even better limits on the masses of the satellites. So that's the sort of the simulations that we've done on the architecture of the system. So I could pause here, and if there are any questions on these 2 simulations, I can go on to the much more complicated simulations where we try to figure out how the 4 satellites came to be, where they are in the orbits that they have. And if there are not, I can go on. Okay. So what we would like to do to understand is how did Pluto and Karen come to be a binary planet, and why do they have these 4 satellites? The mass ratio of the whole satellite system, as I said, it was just under 10 to the 20 grams, to Pluto is around 10 to the minus 5. So they are really inconsequential compared to the masses of Charon and Pluto, and so they're sort of an afterthought rather than the main event. So to give you an idea of how these satellites come to be, I'll start with a protostellar disk, or as many people call it, the protosolar nebula, the nebula out of which the sun and the major planets formed. We have a star in the center here, a little proto-sun, a disk around it, and given that this is an artist's conception, some boulders and some other things that are not so easily visible in protostellar disks today. But one of the projects that I did in my first years at the CFA was to study nearby young stars and to show that pretty much every young star has a disk around it with a radius of, say, 30 to 100 AU, with a mass sufficient to make the planets in the solar system. And what happens once you have this disk, stuff gloms together. In the Northeast, we have lots of hardwood floors, and so you worry about dust bunnies. And dust bunnies form by an agglomeration process, stuff that, hair and, stuff that you skin and various things, glom together and form little dust bunnies. And, in a couple of weeks, you can have a pretty hefty dust bunny that you sweep away. But in the protosolar nebula, stuff globs together, and it goes on for 10 million years. So you can imagine how big this, dust bunnies can get if their things are agglomerating together. And that's how the Earth forms. That's how Jupiter forms. Jupiter agglomerates gas in addition to solids. And what happens with Pluto and Charon is that they formed somewhere in the outer part of the solar system, and their orbits got excited, and eventually they crossed. And so, let's see, I got out of order here. Okay, so anyway, I'll do this. So Pluto and Karen collide, and there are several options for Pluto and Karen colliding. They collide, Charon is destroyed, and you make Charon out of the debris from the collision, more or less how the moon was formed out of the Earth-Moon collision. We don't think that happens in this system because simulations of Charon formation leaves very little room for satellites afterwards. So the idea is that Pluto and Charon collide in a more glancing collision that leaves the Charon intact. Charon takes up an eccentric orbit around Pluto, and then the satellites are either collision debris from this giant impact, or maybe Pluto and Charon circularize their orbits. They evolve into the configuration we see today. And then there's an impact between a trans-Neptunian object or a Kuiper Belt object and Charon, and debris from that makes the satellites. So these are the two models that I'll talk about. So we have a giant impact where Pluto and Charon collide. And I'll show you a picture of that in a second. Charon survives. So here's a glancing collision. Here's Charon colliding with Pluto. And Charon is sort of going from the lower right to the upper left of the diagram in this picture. And Charon loses enough momentum that it becomes bound around Pluto. And it takes up an eccentric orbit. The simulations that Robin Knupp has done suggest that it'll have an eccentricity of somewhere between 0.1 and 0.9. So it has a lot of options there. Its semi-major axis will be from 5 to 10 Pluto Radii. So again, a fair bit of territory there to cover. But you can see in this picture, the artist has cleverly drawn the stuff that spews out from this collision. And that stuff is the stuff that the satellites would be made out of. The other option is to have Pluto and Charon, do their collision thing. They take up eccentric orbits. Over 10 million or so years, they circularize the orbit. They expand into their current orbital configuration. And then, an interloper, a Kuiper Belt object comes along. It hits Charon in a glancing collision, kicks up stuff that eventually gets to this satellite zone here where the 4 satellites are. And the debris from that is sufficient to make the 4 satellites. So we've done a bunch of simulations, numerical simulations, to see whether either of these scenarios is plausible. And if they are plausible, what are the physical properties of the debris needed to make something that will eventually lead to the satellites? So what I'm going to show you is not satellites being made, because that I think is fairly simple once we get material in where the satellites need to be. What I'm going to show you is the simulations of the debris following the collision and what the configuration of that debris is once the system becomes fairly settled. So we have a code that we call Orchestra. It has a bunch of pieces. The main pieces that I'll use today are a multi-annulus coagulation code. I'll describe the coagulation code in a little bit, but the main physical property of the coagulation code for this particular use is collisional damping. Particles collide, the debris particles collide with one another. During that collision, they lose energy and their orbits circularize. Then we have an n-body code, and the n-body code evolves the tracer particles, no satellites, just Pluto and Charon, in response to the gravity of Pluto and Charon. And what Pluto and Karen want to do, since they're on an eccentric orbits and the debris is on eccentric orbits, is they want to drive the material to regions that are stable in orbit. So, if you have debris orbiting in an unstable region around the binary, that material will get ejected. And so the calculation that we're going to try to do is it's a balance between collisional damping from the coagulation code and ejection from, or excitation from the central binary. So as I said, we have the Pluto-Charon gravity to deal with, and the coagulation code gives the tracers a dEdt, or a change in eccentricity as a function of time, and a dIdt, a change in inclination from time. And those are negative. They're trying to circularize the system and pull it down into a very thin disk. So what is our setup? So the multi-annulus coagulation code, we divide a region, a cylinder, say, into concentric annuli. And within each annulus, we have distinct mass bins. The mass bins are logarithmically separated. So in this, we deal with 0.01 micron to 10 micron particles. We have 28 concentric annuli spanning a reasonable region of the volume of Pluto-Charon circumbinary volume. For the n-body code, we have Pluto plus Charon, and we have 448,000 tracers. And we run this calculation on a 112 processor machine. And so we place 400 tracers per processor, and we have this system run. And so the coagulation code, as I said, gives a dEdt and a dIdt to the tracers. Pluto and Karen try to eject the tracers from the system, and we see where the material ends up after a certain period of time. So the first set of results I'll show you are for a giant impact. This is where Charon hits Pluto, survives, and the debris from that we try to evolve. So we have a binary orbit for Pluto and Charon. The semi-major axis is either 5 or 10 Pluto Radii, which spans the range from the SPH calculations that Robin Knupp has done for the collision. We set the eccentricity equal to 0.2 or 0.4 for the 5 Pluto Radii semi-major axis, or 0.6 to 0.8 for the 10 Pluto Radii semi-major axis. And that spans a fair bit of the parameter space that Robin found that worked in her simulations. The mass in the debris is 10 to the 21 to 10 to the 23 grams. We did that in 5 steps, factor 3 steps. Again, that spans the range of debris that's left over from her major axes of 8 to 32 Pluto Radii. Here is the configuration for those orbits. I only show a few of the orbits. Here's Pluto, this little thing. This is Pluto's orbit going around. This is Charon's orbit, the magenta ellipse. The orange ellipses are the orbits for the tracer particles from an innermost orbit of this innermost orange ellipse to the outermost orange ellipse. And those are, since they're, all the orbits are filled, but it would just be a mush, so you wouldn't really see anything. And the orbits have all 2 pi possible configurations. So the space is filled, and we just see what happens to the stuff. So here is the evolution of one of the systems. We have the semi-major axis, the equilibrium semi-major axis, which is a times 1 minus e squared in Pluto Radii, the eccentricity of material, and it's in 6 different snapshots. Just to give you some reference, these dashed lines are the innermost stable orbit of the binary. These 2 solid lines denote where the current satellites are. So early on, the material has a variety of eccentricities, and some of it is very close, some of it is a little farther away. And you can see this magenta stuff is where you're starting to form a ring of very low eccentricity. As this evolution goes on, after 1/10 of a year, most of these particles inside have moved away somewhere. Some of them have gone into here, and some of them have been ejected from the system. And as time goes on, you can see that the particles move to higher and higher semi-major axis. Some of them fall into a disk. You can see that at 100 years, there's a fairly well-defined disk. And then there's a bunch of particles out here that are leaving. So throughout this evolution, there's a contest for a given particle of whether collisional damping can circularize its orbit and have it land in this disk before the binary ejects it from the system. So these particles up here in the top upper right of the lower right panel are on their way out after 1,000 years. But there is a stable disk. And to give you an idea of what that looks like, this is at 1,230 years of evolution. And we stopped it here because not much is going to happen. You can see that the inner part of the system is cleared out. These 4 cyan dots are the positions of the satellites. They're not there in this calculation, but just to give you an idea of where the material is relative to their orbits. We only have 56K out of 448K tracers remaining. So you can see that roughly 90% of the mass has been ejected. But there's a fairly nice ring. It extends outward. And I'll show you the surface density distribution of this material in a little bit. But you can see that we make a stable region. These orbits are fairly circular, and they will not be perturbed over the age of the solar system. And these are small particles, meter size, 10-meter size. And the likelihood is that they will glom together and make satellites. It's not clear how big the satellites will be, but they will be satellites there. So the other simulation that we've done is what we call a large impact. And here we have the binary orbit in its current configuration with a period of 6.387 days, E of 0, and we put mass and debris there. We give it a mass of 10 to the 20 grams. We've tried more, it doesn't really make much difference. And so that's similar to the mass of the known satellites. Again, we have a similar orbital configuration to what we had in what I showed you for the other simulation. We have, the debris has semi-major axis ranging from 2 to 135 Pluto Radii, which we get from a dynamical argument. These orbits have paracenters that just cross the orbit of Charon. So they're very eccentric orbits again. And here's this evolution. We have, again, eccentricity as a function of this equilibrium semi-major axis in Pluto Radii. We start out with a dense knot of material with very high eccentricity and very close to the system. And even after 1,000th of a year, there are a bunch of particles leaving the system. These are on their way out. After a few days, there's still a bunch of particles here, but collisional damping has brought a few particles into a ring. The ring is very close, 20 Pluto radii instead of where we want to be, which is 40 or 50, but that's not very long. 10th of a year, you can see that this ring has moved outward to now 30 to 40 Pluto radii. There's still a bunch of tracers on their way out. There's another set of tracers sort of in between, and for these tracers, collisional damping is trying to get them into a ring. Oh, it's farther out. Some of them will make it and some of them won't. After a year, we have a very nice ring and a bunch of particles on their way out. 10 years, 100 years. In the lower right, at 100 years, we have a few particles left close to Pluto. Those will go away shortly. And we have material, there's material extending from roughly 50 to 100 Pluto radii. And a lot of this material will go away, probably all of it. And here is the top-down view of the system. Again, the 4 satellites sit there. This ring forms farther out. Pluto and Karen are more highly separated. But this is a pretty nice ring after 100 years. And this material is on pretty circular orbits. And it's not going to go anywhere. And again, it's meter-sized to 10-meter-sized particles. And the hope is that they'll glom together like icy particles will everywhere else in the universe, and make satellites. To give you an idea of the surface densities for these as a function of Pluto Radii, the green and the orange curves are from the giant impact model. You can see that there's a fairly extended disk. These are both 10 to the 21 grams. And they lost 80 to 90% of their material. So they're not 10 to the 21 grams anymore. But they have a peak. Their peak is somewhere in the what we call the satellite zone, denoted by these 2 vertical gray bars. And an extended disk that extends well outside where the satellites are. The green dots are for a less eccentric binary, 0.4 instead of 0.6 for the lower one, and a closer binary with a smaller semi-major axis as opposed to the larger semi-major axis. But you can see that, and all of the simulations look like this, actually. Depending on what eccentricity you choose, there's always material in the satellite zone and a fair bit of an extended disk outside. For what we call the large impact, the purple dots, it's a much more well-defined ring. It's a little too far out. And I think if we started with about a factor of 2 more mass, we could get it to be a little closer in. And we're working on that. But still, we have material pretty much where the satellites are in nice stable orbits. And so the results are that a giant impact leads to an extended disk, and a large impact leads to a narrow ring. And these two, you might think that, well, it doesn't make much difference, but there are several issues with both. So for the giant impact, in the giant impact models that we do, Pluto and Karen are a very compact binary with a period of a day or 2 instead of the current 6.5 days. So that binary has to expand. As it expands and circularizes, material that's in orbit around it will experience various resonances. And once, say, the 2-to-1 resonance or the 3-to-1 or the 4-to-1 resonance with PlutoKaron, passes through the satellites, that material will leave. So the worry is that this extended disk won't be able to last through through the expansion of the binary. The other issue with the extended disk is that there's a lot of material outside what we call the satellite zone. And that material could form satellites. And hopefully JWST will place limits on what satellites are allowed. The large impact leads to a narrow ring, which is great because the satellites are in a narrow ring. And if we can get the narrow ring placed well, then we don't have to worry about an expanding binary because it's already done that. And if we can make the satellites form, the question is, can we make 4 of them in the right place? So the next steps in our project are to see if we can actually grow satellites, the right number of satellites, the right sizes of satellites in these disk or rings, and whether there's material outside the satellite zone that JWST observations can detect. And my last scientific slide is that, between TESS and Kepler, there are now about 20 known circumbinary planets. And more are expected. And people, now that people sort of know what they're looking for, it's expected that there will be more and more of these circumbinary planets. And there's a European mission called Plato that hopefully will expand on this. But Pluto is, as the closest circumbinary planetary system, really gives us a nice test bed for understanding theories of how circumbinary planets can form. And so we're hoping that we can apply what we have learned for the Pluto system to these circumbinary planet systems, especially the rocky ones. So to conclude, I think that what I've tried to tell you, describe to you, is that Pluto really is a fascinating system. I'm not a geologist, but the geologists love Pluto and Charon and the satellites because there's a wealth of fascinating stuff going on. They have glaciers and they have Pluto has a little atmosphere that comes and goes. And for those of us interested in planet formation, Pluto is a great system for understanding how planets form, how satellite systems form. And whether you want to call it a planet or not, it doesn't really matter. It's really fascinating that we can try to learn about this system and learn about how the Earth formed at some level and how other planetary systems formed. And so I can reminisce a little bit about Illinois. When I arrived in 1978, in the fall of 1978, and our offices were in the basement of the observatory, in the basement where the Great Refractor is. I don't know what's there now, but we were there, and we were called the basement crew. And we had the offices were nice because they were very isolated from the rest of the observatory. Not all the student offices were down there, but for those of us who were down there, it was a nice, isolated spot where we could, commune and we could chat. And when we felt like it, we could go off to Trino's and have a beer and have a calzone or a pizza and just talk about whatever we felt like talking about. The basement did have its problems. There were the moths, there were the ladybugs. There were a lot of old journals down there, and it was rather dusty. So we were very happy when we moved to the advanced computation building, as I remember, just a little bit. I forget what direction it is, but it's a little bit farther from the campus than the physics building, and that was much nicer. It was closer to some interesting things. It didn't have any moths and it didn't have any ladybugs. And Alan Worth and I shared a nice first floor office to the consternation of some faculty, as I remember, because we managed to lay claim to that and move our stuff in before some faculty were able to lay claim to the offices that they wanted. But Alan and I Alan was graduated 1 year before me, and Jay Gallagher was his advisor, and we had a lot of, Deidre Hunter was next door, and we had a lot of good times there. And what was nice, as I remember, is that it was not too far to the Courier Cafe. I don't know if my understanding is the Courier Cafe doesn't exist anymore, but maybe it's been resurrected. But that was a great place to have a snack or a lunch or even dinner sometimes. But they had one of the best sets of milkshakes in central Illinois. And so we really enjoyed going there in the heat of the summer. And that was one of our favorite places. So I think I'll stop there, and I can take questions about Illinois, or I can take questions about the talk. And I would like to thank the faculty of Illinois that I worked with. I worked with Jim Truran starting off, and Jay Gallagher and Ron Webbing, and they were really great. We had great conversations, whether it was in the old building, the old observatory building, or in the new computation building. And it was a great place to learn about how astrophysics was done. And I think it gave me a lot of tools to work on other problems other than symbiotic stars. I kept symbiotic stars going for a little while, and I still dabble every so often. But I worked on discovering disks around young stars, looking for rotation in disks, doing planet formation calculations, And I think Illinois really helped give me a good start there. So thank you.
Thanks very much, Scott. And as Cassie noted this, I believe the courier is still there. I know my wife likes the egg creams, and so I can testify to the milkshakes. Okay, so do we have any questions for Scott? Yes, I see Yue.
Hey, Scott.
Hi.
Thank you very much. And it was nice seeing you again.
Good seeing you too.
Thanks. So I have a science question. So you must have considered it when you're simulating the dynamical instabilities of the system, given the very eccentric orbit of Pluto and Karen. Have you, or is in the effects of the Neptune and other giant planets in the solar system any significance to affect the dynamical stability of the satellite systems?
Yeah, we have worried about it, and a student of Hagai Peretz published a paper on it. We've done our own simulations, which we haven't published because Hagai got there first. But he did some simulations, and the giant planets don't really do much because the Hill sphere of Pluto is Pluto-Charon is around 1,000 Pluto Radii, and Hydra is at 60. So it's really hard for the giant planets. I mean, that's just sort of a back of the envelope way of saying that the giant planets don't do much. And if you include the giant planets in the simulation, they have no impact. We can't even see that they do anything. The sun is another matter. Outside, I don't remember exactly the number, but outside of around 100 to 200 to 300 Pluto radii. So I think it's more like 300 because it's about 5 or 6 times the orbit of Hydra. The sun plays a role. So even though Pluto's Hill radius with the sun is 1,000 Pluto radii, outside 300 to 400 Pluto radii to 1,000, because Pluto has an eccentric orbit, the sun does play a role, and it pushes that material away. That material is just ejected. But inside, at 200 to 300, there's still some issue of what really stays and what really goes over what time scale. But inside 100, things are pretty safe from the sun. And we did extra simulations with the sun. And the results were no different. The system was dynamically unstable whether we had the sun or not. And the sun didn't seem to add any instability to the system.
Okay, thank you.
Brian.
Hey, Scott. So great to see you, and I enjoyed your talk very much. So if I followed the first part,
it's great to see you too.
When you found that the configuration now is sort of marginally stable, as I understood the game you were playing, they need to all the 4 moons have to survive for the current age of the solar system. So is it conceivable that these impact events could have happened later on, so they don't have to have survived for quite as long?
It's conceivable. It's less and less likely as time goes on because the density of things that can happen, that can make things happen goes down. And the most popular model for the formation of the solar system involves the migration of the giant planets. And so, it's called there's the Nice model and there's the Grand Tack model, and it may have another name by now because they've added more stuff to it. But anyway, the idea is that the giant planets formed in a more compact configuration relative to their current configuration. Saturn and Jupiter don't move very much, but Uranus and Neptune move out. And that migration populates the resonances in the trans-Neptunian region that we see. And so you want Pluto to be formed before that happens so that it can be transported, if it needs to be, into the 3-2 resonance, and then the satellites can form. There's dispute over whether or not the satellites can survive the migration. You can imagine they're in circular orbits, they're not very big. And so, definitely if they hit something on the way out, that wouldn't be good. But that's supposed to be, the migration is supposed to be done during the first 100 million years of the solar system.
Okay.
They have different times depending on what they want to do. But the idea is that it's done by then. And so that doesn't give you much extra time. Another 1/10 of a billion years is no big deal. And so, from this, I think we have a pretty good upper limit. But as I said, the masses could be a factor of 10 less, and the system would be stable forever.
Cool, thanks.
Leslie.
Hi, Scott. Quick question about the exoplanet binary planetary systems. I don't know much about them. What's that population look like, and does that lend any preference to formation mechanisms?
As I remember, most of the exoplanet, circumbinary exoplanets, and now these are circumbinary. There are also exoplanets in binary systems where they're orbiting one star or the other, and I don't remember the details of those. But the circumbinary ones are mostly gas giants or ice giants, because those are the easiest ones to find. And there's more ice giants than gas giants, just like there is in the rest of the exoplanet population. There as yet are no terrestrial circumbinary exoplanetary systems. But Dan Fabricki and a student worked out that they would certainly be stable, but then they wouldn't have been easily detectable in the observations that have been analyzed so far. And so they worked out some methods to improve the detection, likelihood of terrestrial planets in circumbinary systems. So that you don't need, obviously you need a lot of data because you've got the binary and you have this stuff around it. And so getting the transits to work out is, and detecting them is not so easy. They've detected very big transits with ice giants and gas giants. But they worked out some techniques, I don't remember the details, to improve the ability to find terrestrial circumbinary planets. So hopefully people are busily applying those, and we'll see the results of those in the next few years.
Thanks.
So Charles Gammy had to leave early, but he had a couple of questions he wanted me to ask. So in what sense is any of this work computationally limited? And I think by that he means, do you need all 400,000 particles in order to get the results you did?
So I should just say, for the dynamical calculations I do at the beginning, those are not very computationally intensive because it's only 15,000 tracers for the calculation we're trying to figure out where satellites are. And when we do the masses, it's only the 6 objects. So that's, doing a gig a year is not easy. It's mostly being patient. But the calculations where we try to figure out what happens to the debris, we pretty much need all 400, we do 448 because we're on a system with 14. There's a reason for that number. Everything has to be divisible by 14 or 28 or whatever. But anyway, since we lose 90% of the tracers, it's hard to start out with many fewer. If you started out with 100,000, then you're only left with 10,000 to carry the mass, and you're much more prone to small number statistics. And also, each tracer the way we do it, each tracer carries mass. And so the more tracers that we can have, the more sensitive we are to what mass is left over, because each tracer doesn't carry one particle, it carries a bunch of particles. So we have 10 to the 20 grams in meter-sized particles. So that's 10 to the 14 or so particles. And so each tracer carries that some fraction of the 10 to the 14. And the fewer tracers that we have, the more mass each one carries. And so it's when one of them leaves, it's even more heart-wrenching because you have less and less mass with the satellite. So we haven't tried doing more than 400K is possible, but because these calculations only took about 2 or 3 weeks, up to a month on 112 processors. That's not much, but I think we're pretty safe in what we say. And I think going smaller would be hard to do reliably.
So I think that answers his second question is the debris self-gravitating? And it sounds like the answer is yes.
The debris is not not in the sense of that he might be thinking about self-gravitating. The debris has mass.
Yeah.
And so there is gravity between the debris, but it's not, it is self-gravitating. It's not gravitationally unstable, I guess.
Right, okay.
There's not so much debris that is gravitationally unstable, but there's enough debris, the debris has mass. And so the collisional damping actually does do something.
Yeah.
And there's enough collisions, since the collision rate and the damping are proportional to the mass, you need enough mass to make the damping work. And if you have, if you started out with 10 to the 10 grams, say, instead of the 10 to the 20, all of it would go away. So you need enough mass to make collisions numerous enough and effective enough. So it does need to be self-gravitating.
So do you do anything special for the collisions? I mean, do you regularize close encounters or something like that?
Well, so we have, it's a two-part thing. So the collisions are set by the coagulation code. So that's a statistical code. And so you have a bunch of mass bins, and every mass bin ranging from 1/100th of a micron up to 10 or 20 meters has a number of particles at a cross section. And the collision rate is set by the standard, gaseous kind of, kinetic theory of n sigma v. Mm-hmm. And so you get a collision rate. And that collision rate coupled with a collisional damping algorithm gives you a dEdt and a dIdt. So we don't attempt to resolve collisions with the n-body code because that's too difficult. We resolve collisions between the tracers and PlutoKaron, but nothing hits PlutoKaron pretty much. Pretty much everything is just ejected. And we don't worry about whether or not an ejected particle hits something on the way out, aside from this n sigma v. So we've tested this algorithm, and we take very short time steps. So we're always calculating dEdt and dIdt on very fast cadence. So the particles can't move much before dEdt and dIdt change. So there's a constant changing of that. So the particles do react to the changing mass volume characteristics of the system, but the tracers do not collide with one another.
Okay, thanks. So are there any other questions? Not seeing any hands. Okay, well, thanks very much again. It was a great talk, and thanks for your reminiscence.
So I wasn't sure if, because Rebecca had told me that the group might want just a chat tomorrow afternoon, and I told her I was free at 4 or 5, and so if that's interesting, I can do it, and if not, that's also fine.
Okay. Yes. Well, I think we haven't really organized that, but we can certainly. I can certainly.
Okay, well, that's also okay. I won't feel hurt if it doesn't get. I know that everyone has things to do, and these Zoom things are complicated. So.
Okay.
But if someone did want to chat, they could just email me, and I could schedule something.
Okay, that sounds good. All right. Thanks again.
Okay, thank you. And thanks to everyone for coming and staying to the end.
Thanks, Scott.
Take care. Bye-bye.
Bye.